Okay, so as you can see from the title of your note, that what we're going to do in this lesson is revisit a couple of functions that we studied earlier in the year, the linear function and the exponential function, and we're going to compare the graphs of the linear, the exponential, and the quadratic functions. We're going to use the characteristics of and the shapes of each of the three different kinds of functions. And we're going to use those not only to sketch graphs, predict behaviors, but also use a table of values to determine what kind of function is being represented. And so what you can see on this first page is the three kinds of functions that we've now studied. The first is the linear function, and its equation takes the form y equals, or f of x equals mx plus b. M is the slope and b is the y-intercept. Then we go to the exponential function. The exponential function y equals a times b to the power of x, or in this case I've used the function notation because they're all functions, and so h of x, because x is the independent variable, is equal to a times b to the power of x. So you may recall b is the base and a is simply the coefficient, the number that the scale factor of the number it's being multiplied by. And then lastly is our quadratic function, which we've spent the last few weeks working on. Y equals, or g of x equals ax squared plus bx plus c, which is the standard form of the equation of a quadratic function. And we're going to be looking at these three graphs, or looking at tables of values of points to determine which of the three graphs it is. So first and foremost, since all three of these are functions, be aware that the notions of domain and range apply to all of them, and so does function notation, because all of these, as mentioned, are functions. What we are going to do, though, is look carefully at the shapes of each of the functions, and that's going to allow us to determine, given a set of points, which graph we're referring to. Okay, and so we're going to go straight into it. At this point we'll flip over, and what we have here in examples 1, 2, and 3 are three tables of values. So we have a set of x values and the corresponding set of y values for each of the three. And what we're going to do is look for patterns in each successive y value in each of the tables, which will allow us to determine whether the function is linear, exponential, or quadratic. Okay, and so what we'll do is we'll begin with example 1, and what you can see is when you go from 2 to 5, from 5 to 8, and from 8 to 11, there is hopefully a reasonably obvious pattern, and that is that each time we are adding the value 3. Okay, and so in this case, since we're adding a constant value each time, this is going to indicate to us that what this function is in fact a linear function. So we have a constant growth rate, which is linked to slope. Okay, if we look at example 2, then what we can see is we've gone from 1/4 to 1/2, 1/2 to 1, and 1 to 2. And so it's very clear that we are not adding or subtracting, or at least if we're not adding or subtracting the same number, and so that indicates that the pattern suggests that this is not linear. And what we can see is that 1/2 is twice as big as 1/4, 1 is twice as big as 1/2, and 2 is twice as big as 1. And so when we multiply each successive term by a fixed value or base, then that should reveal for us that this is in fact an exponential function. Okay, and so lastly, by process of elimination, we're going to figure that this is probably going to be the quadratic function. What we need to do, though, is identify what the pattern is. And so initially what you'll see is that we go from 2 to 0.5, 0.5 to 0, 0 to 0.5, and 0.5 to 2 again. It does not have a constant factor in terms of a ratio, so multiplication. But what we do have, or a difference. But what you're going to learn today is about something called a difference array, second differences. So what we'll do is we'll take the difference between each subsequent term. So we have minus 1.5 in order to go from 2 to a half. We have minus 1/2 to go from a half to 0. We have 1/2 to go from 0 to 0.5. And we have 1 and 1/2 or 1.5 to go from 0.5 to 2. So those are the first differences. And what we're going to actually do in this case is we're then going to take what's known as a second difference. If we go minus 1.5 and we subtract minus 1/2, we will get minus 1. Minus 1/2 minus a half, and we will get minus 1. 1/2 minus 1.5, and we will get minus 1. And what we have, therefore, is constant differences in the second difference, and that reveals, or that is the tell for a quadratic function. Okay, and so what we have now is, if you look below, each of these statements explains the rule for determining what pattern reveals what kind of a function. So for a linear function, the difference of successive y terms are equal. For exponential function, the ratios, so of course that's multiplying or dividing. And for the quadratic function, we have second differences of the y values are equal. So what we've been able to do now is establish what kinds of functions each of these tables of values represent. And so now what we're going to do is use the table of values to find an equation. So just one clarification point, and that is that for quadratic functions, those are very complicated to find the equations. The focus on this unit will only be finding quadratic equations in the form y equals, or f of x equals, ax squared. So there'll be no bx and there'll be no c term. Okay, and so again, over here what we have are the rules that will assist you in finding the equations of each of these. But what I'm going to do is not read those two, but I'm just going to go ahead and show you in each of the examples. So we're going to go back up here. So for example 1, we had a linear function, and so there's two key factors that we're interested in. First things first, if you were to look at the growth of each subsequent y term, they grow by a constant of 3, and so that actually yields our slope. And then the second important thing is to find b, which in the context of a linear function represents the y-intercept, and the y-intercept of any function occurs when x is 0. So in this case we can read it off the table of values. The corresponding y value is 5, and so that is, in this case, in the context of a linear function, that is b. So we'll just scroll back down, and what we've managed to ascertain is that our function is going to be y is equal to mx, so that's slope, times x plus our y-intercept 3x plus 5. Okay, we're going to go ahead and do that for the exponential function as well. And so for exponential functions, what we're looking for is the base, and then the scale factor, the coefficient of the base. And so once again, what we're interested in our pattern is to the common ratio. So each subsequent term has been multiplied by 2, and so this indicates that our base, so b in this context represents the base. We have a base of 2, and similarly what we're interested in, the function is y is equal to a times b to the power of x. If we were to substitute in 0 for x, it causes this term to equal 1, and it isolates, it gives us the a term. So once again what we're interested in is the x value of 0, which yields for us the a value of 1/2. Okay, and so we'll go down and just make a note of that. And so our exponential function for example 2, y is equal to a, which we determined was 1/2, times 2 to the power of x, 2 being our base. Okay, and lastly we need to determine our quadratic function, and our quadratic function is in the form y is equal to ax squared. And so what we're going to do in this case, so this is the new one, I'll just highlight the rule. We can find a by using the coordinates of any point and substituting them into the equation. And so what I'm going to do for no particular reason is to select the point 2, 2. Okay, and so what we have is the general form of the equation, which is y is equal to ax squared. What I'm going to do is substitute in 2 in the place of y, because that was the y coordinate of the point we selected. 2 in the place of x, because again that was the x coordinate of the point we selected. We selected the point 2, 2. And what we're going to end up with is 2 is equal to 4a, and therefore we have a equal to 2 divided by 4, or 1/2, or 0.5, and so we can write our equation as y is equal to 1/2 x squared. Okay, as one final and relatively quick step, what we should do just to be sure that we've got the correct equation in each case is select one of the points we did not use, substitute it in, and confirm that the function remains balanced. In other words, that will confirm that we have the correct equation. And so I'm going to use the point 1, 8 for example 1. So I've just picked a point from the table, and so I'm going to use the point 1, 8. If I substitute that in, 8 in the place of y, 3 times 1 in the place of x plus 5, and what I end up with is 8 is equal to 8, which confirms the equation is balanced, and that point lies on there. That confirms our equation is correct. Similarly, I'll go back up and I'll select, in this case, I'll select the point 2, 2 again. I won't use 2, 2 because that was the point that we used to find the equation. And so we do have one of our other points here. We have the point 1, 1. And so I'll go back down and substitute that in. So if we substitute in the point 1, 1 on the left, we'll have 1/2 times 2 to the power of 1. And of course, the left and the right hand side equal each other, and that confirms our equation is correct. And lastly, what we're going to do is select one of the points of our quadratic. And so in this case, I'll use the point 1 for x and 1/2 for y. And so I'm going to test using the point 1, 1/2. On the left hand side, the y value is 1/2, and on the right hand side, what I end up with is 1/2 times 1 squared, and once again we have, using a different point, managed to substitute in and confirm that the function that we obtained worked. Okay, so now we have our three functions. Okay, so at this point what I'd like you to do is copy all of these examples down, make sure you've got the correct note, and then turn over. There is a word problem, an application problem, which you have to plot the points and then make a decision about what kind of graph, and then figure out the equation. And so you should go ahead and do that now, and then once you've completed your own attempt, watch the second part of the video and you can check your answer to that.